The question that is solved next is to know if a vector A belongs to a given cone A pi, where the cone can also be given in the indicated form, that is, as the sum of a vector space M rho and a cone N pi. We remind the reader that we use the Greek letters rho and pi to refer to real and non-negative real numbers respectively. This is a difficult problem because non-negative coefficients are involved. However, we will see a very nice way to solve the problem, seeing it from a different point of view. To answer this question, it is sufficient to realize that the dual of the dual cone is the initial cone, that is, we have the relation in the slide. We will see that this idempotence property is crucial to solve the problem. Next, we write the problem of knowing if a vector belongs to a cone in three different ways, and this will indicate us how we can solve the problem. Therefore, we have three ways to view our membership problem. A. Check if the vector belongs to A pi. B. Check if vector A belongs to the dual of A pi. And C. Check if the dot product of vector A by the dual basic vectors gives 0, and by the generators of the acute cone or the edges of the acute cone give values smaller than or equal to 0. Since vector spaces also include their vector change sign, both scalar products must be less or equal to 0, which implies that they are 0. However, when multiplied by the edges or generators of the acute cone, we must get a value smaller than or equal to 0. Then we know how to solve the problem. What we have to do to know if a vector belongs to a cone is very simple. First, we obtain the dual cone of the cone A pi in the form B rho plus C pi, that is, as the sum of the vector space part and the acute part of the dual cone. Second, we multiply the vector A by the B rho basic vectors scalarly and check if they are 0. Third, we multiply the vector A by the C pi edges scalarly and check if they are less than or equal to 0. If any of these things fails, the vector A will not belong to the cone, and otherwise it belongs. Next, we see an example. Given the row vectors of matrix D and the cone A pi, we want to check whether or not those vectors belong to the cone A pi. To this end, we obtain the dual cone A pi super P of the cone A pi using our gamma algorithm that gives these tables, where we have introduced the cone column generators one by one, in iterations 1 to 4. Then we get the final table that contains the basis of one vector of the vector space and the 4 edges of the acute cone of the dual cone. Thus, the dual cone can be written as indicated in the slide, where the columns of the two matrices come from the final table on the right. Next, we calculate the product of matrix D by the matrix H, which contains the columns of B and C, and we get the indicated matrix that contains in the blue column the dot products of the 4 vectors by the column of B, and in the other columns the corresponding dot products by the columns of C. A row vector of a row of matrix D belongs to the cone if and only if the same row in the last matrix contains 0 values in its first column and non-positive values in the remaining columns. Since the only rows that have a 0 in the first column and non-positive values in the other columns are the first and the third, only the first and third vectors of the given matrix D belong to the cone. With this, we end this video and invite you to see the next one that deals with the problem of obtaining the intersection of two cones.